This is the definition of UTC and the International Atomic Time. Now let's go a little bit inside the BIPM, the Bureau International des Poids Mesures, where I work, to see which is the type of computation, the type of activity we have to do to compute UTC. So first, UTC is computed at the BIPM in the third time because we need time to collect all the data and to validate everything. While there are laboratory, National Meteorological Laboratory, Astronomical Observatory or other time laboratory, which are realizing approximation, real-time approximation of UTC, which are called UTC-K, where K is the name of the laboratory. So we said we base time on atomic clocks. In this moment there are about 450 atomic clocks kept in about 80 laboratories all around the world. So we have so many clocks and we make a sort of ensemble average to define the ensemble time. The clocks are not moving and we have to measure their difference because we want to have the clock all synchronized, and if we want to define an ensemble time, we need to measure one with respect to the other. This type of measurement is mostly based on GNSS. So you see that GNSS is based on clock and timekeeping is based on GNSS. We have a mutual relationship in between these two types of systems. The most used comparison is based on GPS with a receiver connected to the clock, very special, precise clock. You can measure the difference with respect to a certain satellite clock. Another laboratory measure in the same moment the difference with respect to the same satellite clock. Then you exchange the data, you make the difference, and you estimate the difference between the two remote clocks. This is the basic idea. We can do something more. We can use GNSS and we can have an accuracy of a few nanoseconds. We can use a little bit more evolved type of GNSS measurement using not only the GPS but also the Russian GLONASS, the Chinese Beidou, and the European Galileo. And we can have additional algorithms able to improve this type of measurements. Or there are other techniques which are called two-way time and frequency transfer technique based on satellite, where the laboratory is sending a signal to the satellite, which is jumping back to the satellite. It is again transmitted to the satellite and coming back. This system is said to be passive because you just receive the signal. In this case, you have to transmit and receive and transmit back. So it is a little bit more complex, and in this case also new development are in progress. And also some connection by optical fiber are under development in different parts of the world, and this will help in having an even better capacity for time and frequency transfer. So let's come back to the BIPM. At the BIPM we have 450 clock, we have time transfer measurements. All these measurements arrive to us every month, and we make a sort of weighted average, which is called a shell atomic libre, which is optimized in stability, which means that the clocks are weighted proportionally to their stability. We have many clocks, we make an ensemble, and the ensemble time is not jumping, but it is very, very stable. Maybe it is drifting away, it is not accurate, but it is very stable. So we have a second step. You remember I spoke of the primary frequency standard, these structures which are very complex and very accurate. They are the reference for calibrating the ensemble time that maybe is drifting away. As you see there, it was going down and measured by the primary standard and so corrected to be as much as possible accurate. So the second step, which gives origin to the International Atomic Time, is based on the weighted average, the stable weighted average, steered, corrected by comparison with the primary frequency standard to have the international atomic time, which is stable and accurate at the level of 10 to the minus 16. Then the astronomers, the institution related to the Earth observation, measure the Earth rotation, decide when it is time to add 1 second, and so we get UTC, the Coordinated Universal Time, which is the last step of our computation. And what we measure and what we publish in our famous BIPM circular T is the difference between the international UTC and each local real-time approximation. So our main results, which comes out every month, you see the circular T, for example, which was published in May 2021, contained the data of April. We have 1 point every 5 days, and this is UTC minus UTCK, where we have here 80 laboratories. We start from the first one, AOS in Poland, and you see that the difference of this UTC local time scale with respect to UTC was in the region of 1.5, 1.8, 1.7 nanosecond with this uncertainty. So you see that depending on the type of the laboratory, we can have different values. The best laboratory can remain for years within 10, 20 nanoseconds with respect to UTC. Consider that when you realize your local time scale in real time, UTC does not exist yet. It will exist next month. So you define your local time scale like a prediction of UTC, and only after 1 month you see how good your time scale was and your prediction of UTC. In the last years, we have also started to compute a rapid version of UTC, which is called UTC Rapid, and these results are available every week on Wednesday and contain the results of the previous week. You can find here all the information and all the products that we evaluate and that we put at disposal of the entire time and frequency community. And there are many information. For example, here on this plot that we update every month, you can see which are the primary and secondary frequency standard. For example, the cesium fountain I was telling you before, realizing the second with 10 to the minus 16 accuracy. They are realized in this laboratory and they are available in this month. Some of them are available almost every month. Others are available a little less frequent. Optical standard, the one I told you 100 times more accurate, are available. They start to be available. You see, in the last 3-4 years, we had some calibration also obtained by those laboratories, mostly based on strontium and ytterbium optical standard. And this is a plot which gives the idea of how many of these very important and very complex frequency standards are available. Other data and other possibility of dynamic plot are on the website. You can see, for example, which is the offset between your time scale and UTC. You can also check which is the measurements between a time scale of one laboratory with respect to that of another laboratory, comparing different techniques. In this case, for example, the blue is obtained with Galileo measurements and the black is obtained with GPS. In this case, it is the two-way time and frequency transfer with respect to the GPS precise point positioning. So many other data are available. One important research activity is on data processing, on algorithms, and I will give you some example of the analysis of why these periodical fluctuations are observed on some UTCK and on UTC, and we were able to understand the steering, the fact that UTCK is corrected to be in agreement on UTC gives origin to this behavior. Another study was evaluating how good the clock are predicted. In fact, I did not tell you, but in the ensemble algorithms, we need to predict the clock, and the prediction has an error which grows with time. So when you predict for 1 month, the first day you predict quite good, but at the end of the month you can have nanosecond error in the prediction. And also a recent development on algorithms is based on a new way to use time transfer link between the clock. Because, for example, you see here in Europe we have several laboratories. They are compared by GPS, they are compared by Galileo, they are compared by two-way satellite time transfer or by optical fiber. We have redundant measurements, and these measurements at the moment are not fully used. So a new development was performed, giving rise to this new treatment, which also allows to take into account correctly of laboratory which are not calibrated. Calibration of the measurement system is fundamental in timekeeping. And you see in the circular T we have a laboratory with 20 nanosecond uncertainty, but it is not really 20. It is just that they were not calibrated. This value will be corrected in the future, correctly taking into account the not calibrated laboratory. Also on TimeLink we have a certain number of research projects. As I said, time transfer is based on classical GNSS with mostly the precise point positioning and two-way satellite time and frequency transfer, which have a stability at the level of 10 to the minus 16 in relative value. If we want to compare optical clock, we need a measurement system of clock at distance which is better than this one. And so advances are possible either with the two-way or with the GNSS, with two techniques that are currently under investigation. The first one is called software-defined radio receiver, where the two-way processing of the two-way measurements is based on digital data and not only on the receiving the analytical signal, the analogical signal. And this type of process is improving the stability and reducing diurnal fluctuation. And so since 1 year now, we are using in UTC this type of measurements together with the classical two-way. And also we have launched a shared platform for developing together this type of digital analysis. Concerning the GNSS, we mostly use precise point positioning, but there are sometimes jumps from batches of data which are due to different reasons. And one of the reasons is the fact that the measurements we use are also related to the phase of the signal, and the phase has cycle ambiguity. We don't know which cycle we are measuring. And knowing which are the setup of the system, we can know that the discontinuities due to the phase jump has a certain value that can be 1 cycle jumps or 2 or 3, but they are integer. So this is why we have integer precise point positioning, which has now been tested with respect to the most precise time transfer, and we see that we can reach 10 to the minus 17 at 20 days or 1 month of observation time. So this is getting better, still not enough to measure the optical standard, but progressing. And here, for example, you can see the difference between two time scale, the Swedish and the German one, measured for 10 months by the classical two-way system, by the integer PPP, and by the software-defined receiver. You see the behavior exactly the same, and you can see the reduction of noise of the 3 different techniques. Also, since we have not only GPS, but also Galileo, GLONASS, and Beidou at disposal, we are evaluating the possibility to have a multi-GNSS precise point positioning, and still a lot of work is to be done. We are just at the beginning.